Okay, so let's get started today. Have several things on the docket for today. We got make files. We have creating a class when one or more parameters is not known until runtime. We have random shuffles, like shuffling a deck of cards, and then we have hashing. But first, is there any questions about the current lab? We getting it? Or we haven't started it? Hopefully we've started it. Okay. Okay. Well, in that case, you'll have noted that last time we talked about separate compilation, which is that with separate compilation, you put your code into two or more files. You had to compile all of those files together in order to get an executable. So last time the example was that we might have a roster.h. What does roster.h contain? What kind of code? Definitions. So declarations, it contains class declarations, but it does not contain method definitions. So then you might have a roster.cpp, which would implement the methods for the roster class. So this would simply, roster.h would be the roster class declaration, but would not contain the method definitions. And then you would have typically a driver program. So we'll call it, say, roster main. And I know that Dr. Plank had slightly different names because he was doing multiple iterations. So he had like 1, 2, 3, 4, 5. Okay, and if you, it's certainly fine to write G++ O, say, roster main, roster.cpp, roster main.cpp. But when you do that, it recompiles both files even if you only changed one of the two files. That's not a big problem in this class because your files aren't that big. But in the real world, you might have hundreds of files, and if you change only one file, it's kind of inefficient to have to recompile hundreds of files that were not changed, right? That's kind of wasteful, could take a lot of time. So you have this concept of separate compilation where you separately compile each of the files. And the way you can do that is with the -c flag. It says compile the file, but don't make it executable just yet. And what is the suffix of the files that, what's the name of the file that these things are compiled into? So what would be the name of the roster.cpp file that has been compiled? Roster.o, very good. So the compiler will compile these into what are called .o files. And then you have a separate step which is called the linking step. So this is the compilation step. And then you have the linking step. So typically, what you would do in the real world is, let's say that you made a change to roster main, but you did not change roster.cpp, then you would only execute this statement and this statement, the statement that compiles roster main and the statement that links the two .o files together. Again, this is very simple at this point, but in the real world you may have hundreds of files that you need to keep track of. And so there is what is called project management software that you can use to automatically track which files need to be recompiled and then does the relinking for you. And Make is one of those project management software tools that Dr. Plank is fond of. And the idea is you provide a set of rules that define which files need to be compiled, and what Make does is each time you invoke it on a so-called makefile, so you provide what is called a makefile, and it contains the names of the files that should be compiled, plus commands for compiling and linking these files. Because you don't always want to compile them in C++, there's other languages, so it needs to have rules or commands for compiling and linking. So Dr. Plank is providing you with makefiles for the different labs. So if we go to lab directory for his lab 3, you find that there is a makefile there. Should be a makefile. Although I'm not seeing it. Yeah, I don't see it there either. Well, let's go to him. Okay, I guess he didn't provide a makefile for lab 3 yet. Okay, let's go then to his notes. And it's not there either. Okay, I was looking for a link. Ah, this is annoying. There we go. Here's a makefile. Looks pretty complicated. Okay, so here's the names of all the files. Okay, and that's actually the names of the executables that he's going to create. And then down here, you can see that there are certain rules for compiling things. So this rule says that the name of the executable is roster01, and that it's going to be created from these three .o files, and that this is the command that's going to be used to link those three files together. Now, in order to create these .o files, there has to be rules for creating them. And it turns out that this is a rule. It says for any .cpp file, it can be converted to a .o file using this command, g++-c, the name of the file .cpp. So it's fairly arcane. We don't expect you to be able to write these make files, but Dr. Plank provides them for you on occasion. What happens is when you execute make and you provide the name of the make file, is that it will check to see which files are out of date, and whichever files are out of date, it recompiles them automatically while not recompiling the ones that are up to date, and then it creates an executable. Okay, and if you omit the name from make, if you just type make, it still works because it automatically, in that case, looks for a file that's called makefile. By default, it looks for a file named makefile. So if you just say make without saying anything else, it automatically looks for that. So that's why it works when you type make. Okay? So any questions about make files? I'm not going to test you on them, but I wanted you to at least be introduced to what they are. Okay, so that takes care of point number 1 today. So we move on now to creating a class when one or more parameters is not known until runtime. So Dr. Plank eventually, as he's developing this roster program, remember he goes through a number of steps. First he reads the names in, then he's going to chop them up into columns, then he's going to add HTML code, and then he's going to add a random shuffle. Well, for his first program, his first program is a very simple one. Okay, he just creates it and he opens argument 1, he's done. But then he moves on to the second step, which is where he's going to turn the names into HTML. And in order to do that, he needs to break his names into columns. And one of the arguments to the program is going to be the number of columns. Now he's going to have to create, just a second, a function that takes the columns and breaks them up. There's no real big trick here, okay? Other than that, a good way to create things in columns is simply to keep counting. So keep a counter, which in this case is I, and let's say there's 3 names per column. So he just starts counting 0, 1, 2, 3, 4, 5, 6, and every time and he mods I with the number of columns, which in this case is 3. So every time that this result becomes 0, he knows that he's starting a new column because it is flipped over. So you yourself can tell that 0 through 2 should go in row 1, 3 through 5 should go in row 2. And sure enough, if you do 0 mod 3, that's 3, so that's the first row. 3 mod 3 is 0, so that becomes your second row. And 6 mod 3 is 0, that becomes the start of your last row. So this technique of using the mod operator is very useful for organizing things into columns. It's a recurring theme in this course. So it's a pattern that we talk about design patterns often. This is a design pattern for columns, that if you need to organize your data into columns, the mod operation is a very convenient way for knowing when you should start a new row. Okay, so that was step 2. Then in step 3, he decides that he's going to add a constructor, and he's going to add yet another command line argument, which is the starting number of the first picture. And for the first time, he's going to store this command line argument as an instance variable in his class. So you can see that he has created a constructor. Does anyone remember what are the 2 things that distinguish a constructor from any other method? There's 2 ways in which a constructor differs from any other method. Its function prototype will differ. Yes.
It has the same name as the class.
Very good. Same name as the class. And the second one's a little more subtle. Very good. Does not have a return type. Those are the 2 things. Okay, so that's how you know that something is a constructor. Has the same name as the class, does not have a return type. Okay, so he's adding this new constructor, and this variable start is going to be the number for the first JPEG file. So his JPEG files are going to be numbered. In this case, the number he would input on the command line would be 1001 to indicate that that is his first number. So he's storing that number as an instance variable. Okay, so it's very simple. He simply is assigning to start this starting number. So changing roster.cpp is very simple. However, he now has an issue, which is that what would happen if if he tried to say right here, roster r argv2. First of all, let's suppose that argv2 doesn't exist. What do you think is going to happen? Let's say the user hasn't provided enough command line arguments. Okay, we're going to start calling in the back. What do you think happens? Just take a guess. Okay, don't have an idea. It's probably happened to you though. Segfault, very good. It will segfault. So that's no good because segfaults don't give the user meaningful information about why the program crashed. If the program has bad input or insufficient input, we want to give the user meaningful feedback about what they did wrong, and segfault does not give them meaningful information about what they did wrong. So that's the first problem with passing argv2 right there, is we don't even know that it exists. But let's say that in fact it does exist and it's a valid number. Okay? More subtly, the compiler will still give you an error message here. Okay, what is the type of argv2? Is it an integer? It's a char star, it's a string. But the constructor expects a what? Does it expect a char star? Expects an integer, doesn't it? So the compiler would give you an error message here because it would be unable to convert that string to an integer. So there's multiple reasons why it's no good to declare roster here. So Dr. Planck says, okay, there is a solution. And he calls it roster 03 evil. So what he does is he simply defers the declaration of R until after he has done his checking of the command line argument. So there he checks the argument to make sure it exists. I know earlier I said argv2, but it's really argv3. So he first makes sure up here by doing the check of argc that there's enough arguments. Then he checks to make sure that it is an integer and that it's a number that is a positive integer. Only when he is sure of that it is a positive integer and he has it stored as a positive integer does he declare the variable and pass it to the constructor. Now, Dr. Planck rants against this way of doing things. Why is Dr. Planck not a fan? Okay. Man in blue. What's your name? Michael. Do you know why he hates this? Okay. In the kind of green vest and white arms. What's your name? Dave. Dave?
No, Dex.
Dex.
I'm not really sure why.
Okay. Anyone have an idea why Dr. Planck doesn't like this style of programming? It will compile and it will run. Yes.
Would it be because it'd be hard to find if you're searching for it?
Yes. He feels that variable declarations should all be placed at the beginning of the program. And he believes that it is hard, if you don't do that, it's hard to find the declaration of the variable. So if you know that all declarations are at the start of the program and you're looking for a declaration, you can easily find it. Now, Dr. Planck is old school and he uses VI. In the real world, you will use something called integrated development environments like CodeLite. And in those integrated development environments, all you have to do is hover the cursor over the variable and it will tell you what its declaration is. So I am not as hardcore about this as Dr. Planck is. Okay? So I don't care if you put your variable declarations in the middle of your programs. However, when you reach 302 next semester, I will not be your instructor. Dr. Planck will be. And this is a big bone for him. There are small bones to pick and there are big bones. Dr. Planck considers this a big bone. So should you get in the habit of putting your variable declarations in the middle of the program, make sure that over the summer you forget this nasty habit because in 302 he will mark points off for it. I will not mark points off for it here. So at any rate, I'm just telling you what the philosophy is. Different companies have different style guidelines, and whatever company you work for has different style guidelines. So BVZ Inc. doesn't care where you put your variable declarations as long as they precede their first use. Dr. Planck Inc. fires you for putting your variable declarations anywhere but at the top of your program. Okay, so that means that Dr. Planck's examples are going to be very careful to put all of his variable declarations at the start of the program. This creates an inconvenient problem, which is that, as I just showed you, it was impossible to declare roster as at that point. So there's a way to finesse it. Unfortunately, we haven't talked about pointers yet. And in order to finesse it, you have to use something called a pointer, which is a delayed way of creating an object. So the pointer, in essence, says, hey, I'm going to create a roster object. I'm just not going to do it right now. I'm going to do it down the road. Here's where I'm going to do it. So now you have to use this operator called new, and it creates an object for you of type roster. And because we now know the starting number, we can pass that parameter to the constructor, and it creates an object. And if you use a pointer variable, you have to use the arrow. So if you use a pointer variable, so pointer variables, so if you use a pointer variable, you use an arrow, which is a dash followed by a greater than character to access methods. And if you don't, the C++ compiler will complain. So questions about that? Again, if you look for an arrow on your keyboard, you will not find it. It is a dash followed by the greater than operator. No space. Gavin?
Isn't there another notation as well?
Nope.
One-
Oh, yeah. That notation, right? Don't use this notation, please. I hate it to tears. Just like Dr. Planck has small and big bones, this is my big bone. I hate that notation. Just use an arrow, please, if you're going to use a pointer variable. It was introduced for a reason. It makes your code look prettier. That's the other way, though, Gavin. Okay? Yes?
Couldn't you just overload the constructor to accept the cars star?
You could. But the problem is it would still segfault if there weren't enough command line arguments. You still can't get around that little nasty problem. So you're right, you could, and you couldn't get around the problem that if the number was negative, you don't have a check for that yet. So he wants to make sure it's totally okay before he calls. So you're right, good try to get around it, but you can't quite get around it totally. Other questions about this? Okay, so that moves on to topic number 3 for today, which is random shuffles. So this is a common thing that we want to do in computers. Obviously, shuffling a deck of cards is an example of a random shuffle. In Dr. Planck's application, he's reading in these files, they're numbered from 1 to 18. He wants to be able to randomly shuffle the images so that they're not necessarily printed out 1, 2, 3, 4, 5, 6, 7, but instead, maybe on the first row, maybe it's 3, 17, 6, 2, 10, 8, and on the next row, it maybe is 1, 16, 5, I don't know, you get the point. It's a random shuffle, as opposed to being, this is not a random shuffle. This is deterministic. Okay, so he wants a random shuffle. And in his notes, he gives you 3 different ways to do a random shuffle. So the first way is actually an incorrect way. So we're doing random shuffles. And what he wants to do, so he basically has this table. Okay, we're going to number it from 0 to 17 because in this case there's 18 files. But in general, you don't know how long it is. Okay, so what he's going to want to do is assign a random number between 0 and 17 to each of these. Actually, he wants to assign a number between 1 and 18 to each of them. And he would like the numbers to be unique. Okay, he doesn't want a repetition, so it's going to be bad if it's like 3, 8, 3. That's no good. Why is it no good if he has 3, 8, 3? What's going to happen in his final output, Gavin?
It shows up twice.
The same picture shows up twice, whereas some other person's picture is missing. Okay, so they need to be unique. So his first stab, so I'll call it solution 1, is to just generate a random number between 1 and 18 for each of these. Okay, actually, does he generate a random number between 1 and 18 or 0 and 17? Let's see. I'd like to be consistent with what he's doing. D. Come on. 0 and 17. Thank you. So he is generating a number between 0 and 17. So solution 1 is basically for I equals 0 to 17, generate or set, I'm going to call it set photo I equal to a random number between 0 and 17. So he just calls the random number generator and he gets a random number between 0 and 17. So what do we think is going to be the issue with that? Duplicates. Okay, so there's no guarantee that a random number generator is going to give us 18 different random numbers. In fact, the chances of it doing that are surprisingly low. Okay? You'd have to run the random number generator an amazing number of times in order to actually get it to generate 18 unique numbers. So solution 1 doesn't work because problem. Okay, there almost certainly will be duplicate numbers, which means that some photos will be duplicated and others will never appear. So that's clearly bad. Okay, so we quickly reject it. And I'm not going to go over the code. You can look at the code. I think it's pretty straightforward. So we're just going to go over the high-level solution. So solution 2 says, okay, that didn't work out so well. So what he's going to do in solution 2 is he's going to keep track of which numbers have already been generated. So initially, he's going to set everything to false to indicate that none of the numbers has yet been generated. Okay, so he's basically keeping an array that's going to tell him whether the number's already been generated. And he's going to call that array, what's he calling it? In random. So he's got 2 vectors. The first one he is calling random, and the second one he is calling in random. So random is the same one that I was calling photo before. I was calling this photo. Okay, so this is where it's going to... So let's say in this next solution, the first random number that gets generated is 3. So he goes in here and he says, oh, currently 3 is false. So we've never seen 3 yet. So we change false to true. But we now know that 3's been generated. Next we generate 17. Has 17 been seen yet? No. So we add 17 here, and we change 17 to be true. Okay, now the next number he generates is 3. When he goes and checks 3, what does he see? It's true. What does that mean? He has to regenerate a number. So that's what he does, is he just repeats it and he generates a new number. What is another technique he could have tried rather than generating a new number? Yeah, you're getting to the next one, but don't decrease the size of the list yet. Take the number out is the same as decreasing the size. Good. This is good, but yes, or add one. Either one. So what he could do is either walk forward or walk backwards to find the first free entry. But that's not actually a really good solution, it turns out. So solution 2 is basically for I equals 0 to 17. Okay, generate a random number. From 0 to 17. And then while in random, so we'll call that R. Whoops, yeah, R equals generate a random number. While in random of R, so while it's true, we have to generate a new random number. R equals generate a random number from 0 to 17. So when we come out of the loop, we know that R is a new random number, so we simply set in random R to be true, or in Dr. Planck's case, I know he sets it to 1, and he sets random of I to be equal to R. Okay? We good with that? You could convert that hopefully to actual C++ code, and if not, Dr. Planck does it for you. I'm seeing knitted eyebrows. You have a question about that, or good? Okay. Now, there's a problem with that, which is as the array gets full, as this in random array gets full, what do you think is going to happen by the time we get up to about number 16? We have to generate a lot of numbers probably in order to get a unique one. Okay, and it can be analyzed. Okay, I'm not going to do it a whole lot with you, but basically the first time through you're guaranteed. So iteration 1, it's guaranteed to be unique. So for 0, it's unique. When I is 1, you have a 1 in 18 chance of having to look again to generate another random number. Okay? After 2, you have a 2 in 18 chance of having to generate another random number. By the time you're up to 16, you have a 16 in 18 chance, or a 8 divided by 9, almost a 90% chance of having to generate another number. And in fact, even when you generate that second number, it's also 90% that it won't be right. Okay, and you can actually figure out that the expected number of numbers that you have to generate per iteration is that one. So the first time when I is 0, it's just n divided by n, or 1. You're guaranteed that it's 1. When it is I is equal to 1, and in this case n is 18, it's 18 divide it by 18 minus 1, which is 18 over 17. It's still not bad. That's pretty close to 1, right? But when n, or I, gets up to 16, now it's pretty bad. Now we have an expected number at 9 before we actually find a unique one. So it turns out you can do some fiddling around. You can reorganize this summation, and it can be reorganized like this. And for those of you who've seen it, this is called the harmonic sequence. And it roughly evaluates to natural log of n. So on average, you're going to end up looking at about n natural log n numbers, which isn't particularly good. Okay, it's not horrible, but it's not great. For 1,000, it means you're going to look at about 8,000 to 9,000 numbers. Okay, so questions about solution 2. So solution 1 just didn't work because it generated duplicates. Solution 2 works. It guarantees us unique name or photos, but it's inefficient. Well, it works, but we can do better. So remember Goldilocks? First one, not too hard. Second one, the bed's too soft. The third one, the bed's just right. So our Goldilocks solution is solution 3, which is what several of you suggested, which in effect is to shorten the list. So you start out and you again have random. And what you do is you actually start at the end of the list. So you start at item 17. And you generate a so initially you just say that the elements in here are in order. So now we want to shuffle them. So what we do is we generate a random number between 0 and 17. Let's say we generate 3. We swap 3 and 17. So 17 goes here and 3 goes here. And then we figuratively shorten the list by next looking at item 16. So we're guaranteed now that 17, the last photo we will output, will be number 3. Now we go to 16. We've shortened the list. We generate a random number between 0 and 16. Let's say it's 1. So now we swap 1 and 16. So now we have 1 here and 16 here. And we just keep doing this. Okay, so now we're at 15. Let's say that we generate 3 as a random number. If we generate 3 as a random number, what we do is we swap entries 3 and 15. This is where we are. So 3 was a random number, but we take the number at entrance 3 and swap it. So this becomes 15, and this becomes 17. So what we're doing in effect is at each step, we are randomly selecting an element to go at the current end of the list, and then we chop the list down by 1. And at the end, we're guaranteed to have a random shuffle. And at each step, how many random numbers do we generate? 1. So that's pretty good. So what we do is actually for I equals 17 down to 1, generate a random number So R equals generate a random number from 0 to what? To I. Very good. There may be that it doesn't change. So it could actually, let's say when we're at 14, maybe the number that gets generated is 14. That's fine. We just do no swap. Okay, so R equal generate a random number from 0 to I, then swap entries or swap random I and random R, and that's it. Pretty simple. Okay, and there's only n random numbers get generated. That's pretty good too. Actually, n minus 1 random numbers get generated because I only went from 17 down to 1. Why didn't I go down to 0? You're right, I don't need to, but what's going to why don't I need to? What would happen if I executed it for entry 0? Yes, the random number I would generate would be 0, right? Because I'm generating a random number from 0 to 0. So I would simply be taking whatever was currently there. There's no reason to do that. Once I got down to 1 and did the swap, the random shuffle was finished. So this is a cute idea. And it's efficient, and it gets them randomly shuffled. Okay. So questions about this one? What's nice about this is it's actually shorter than solution 2, so it's more elegant. I think it's easier to understand, and it's faster. That's what's always we're looking for. It's often the case that faster means longer, but meaning more lines of code. But in this case, faster was actually fewer lines of code. Now, it was more lines of code than solution 1, but solution 1 was wrong. Okay? We're good? Very good. Okay, so we actually come to a major turning point at this point. Up till now, we have been reviewing C++, the part of this course about making you a better C++ programmer and teaching you how to program better. So remember the beginning of the course information. We said, what are the course goals? Okay, so to start becoming self-sufficient C++ programmers. That in part has been what we've been doing the last month by giving you more in-depth review of C++. To become familiar with using command line tools. We're certainly doing that to you by making you use Vim or some other command line editor, by making you use G++, by making you use Unix and commands like cd and ls, by making you use make, so we're getting you comfortable with using command line tools. We've actually, believe it or not, done a little bit of algorithm analysis. We just did that when I came up with n natural log n versus n minus 1 random numbers, so we've done a little bit of that. What we haven't done anything of really is understanding basic data structures, which is what the subject material of this course is all about. And this is what we're going to be doing for the rest of the semester, as well as analyzing how efficient these basic data structures are. And the basic theme for the rest of this semester is going to be, so the theme for rest of the semester is this. How do we organize data so that, one, we can efficiently, well, actually, I don't want to have to keep writing efficiently, so that we can efficiently find a piece of data. So let's say that I want it to find my name in a set of names. So you might want to find a person's name in order to print information about them. 2, insert a piece of data. So I may need to insert a new person into my data set. And 3, delete a piece of data. This is going to dominate our discussions for the next 3 months. And there are a number of data structures that you will be introduced to that do this, including hashing, lists, and trees. Those will be the big ones. We'll also get to stacks and queues. Today we will do hashing. It's the one data structure that you will see before the exam. I know most of you were here last time, but just remember, a week from today is your first exam. It covers the material up through hashing, and then a week from tomorrow you will have the programming part of the exam, which will only cover up through classes, which is what we just finished. Okay, I'll go over that more on Thursday. So, our first data structure that we will be considering that does that is hash tables. Okay, they are a pretty simple data structure. You have already actually in 102 been introduced to a technique for efficiently finding data in an array. Do any of you remember what that technique was? You had a set of data in an array. And it was ordered. What could you do to efficiently find some element in here, like, say, 18? Bisect it. So you use a technique called binary search, where at each point you look at the middle element, okay, which in this case you would start at 2, and at each point you eliminate half of the array. Okay? And you may or may not remember, but this required roughly log 2n searches or probes, where n was the number of items in the data set. Now this is pretty efficient for your find. So remember, we are looking at find, insert, and delete. Well, it turns out that insert and delete aren't particularly efficient. What do we have to do if we want to insert a new item into this array? Let's say we want to insert 17. Very good. You have to shift. If I want to insert 17, all the remaining values have to be shifted one to the right. That's inefficient. Okay? It can take up to n probes in order, or n moves in each case to execute those two, and that's inefficient. If I have New York, 20 million people in the phone book, and I move to New York, the Big Apple. Well, unfortunately, a lot of names got to be moved to put me in there. Actually, not as many to put me in there. Who has a last name that starts with A in here? How about a B? All right. Well, you two break the bank because B comes pretty early in the alphabet. So we're going to have to shift about 18 or 19 million names to get you into the phone book. That's not too good. Actually, they're pretty happy with Vander. I'm kind of toward the end of things. But they're not going to be happy about you all. So inserting and deleting aren't particularly efficient operations. We can do better. And hash tables are our first stab at that. So basically, binary search works well with what we call static data that doesn't change, but it doesn't really work well with dynamic data that's constantly having things added to it or to subtract it from it, which is what happens with phone books. Do it. No, it doesn't mean you get to go. It just means that you don't get to look at Dr. Planck's nice notes. Okay, so here's the idea behind hashing. You start with a vector. Okay, and you're going to, let's say, insert names into the vector. So let's say I want to put Brad into here. Instead of just putting it in the first location or putting it in sorted order, what I do is I apply what is called a hash function to it. And the idea is to create a random number between 0 and, in this case, 9. So I apply a hash function, and let's say it returns 8. How it does it, we don't concern ourselves just yet with it. But it takes Brad. One obvious example would be to assign the characters at their ASCII values, like a capital B might be 96, say, or say 45, and an R might be 100. We add them together and mod by 10. That could be one thing you could do. At any rate, it comes up with 8, so we put Brad here. Then we apply our hash function, let's say, to Smiley. And it assigns her location 4. So we put Smiley into location 4. So the idea is that each time we want to insert a person into our vector, we apply a function to that name, and it generates a random number between 0 and the size of our vector. And we put it in there. Okay, so if we want to find a name, it's pretty simple. So if we are unsure, if we want to find the information associated with Brad, we simply apply the hash function. It returns a number, and we search at that particular location in the vector. Okay, so find is pretty efficient as long as this function is pretty efficient because it spits out a number. We go to that address and look at it. Okay, insertion was also pretty efficient. We simply generated a number. We went to that location and inserted it. And deletion is pretty efficient because we simply go to that location and we delete it. So if we want to delete Brad, we simply generate the number and delete it. Okay, so this is a pretty simple, at least conceptually, this should be pretty simple. Come up with a hash function that randomly computes numbers based on a name, put the name there, and then if we look it up, same idea. So what is one fly in our ointment? What is a possible fly in this ointment? Well, if we generate the same number, let's say we're going to insert Yifan. And let's say that she also hashes to 4. That's called a collision, where two elements hash to the same entry. So we need what is called a collision resolution strategy that's going to allow us to deal with these collisions. And we'll see that there are several strategies that can be employed. But this is a very simple conceptual thing. The we have several elements. Okay, so hash table elements. We have a vector or array. So the hash table itself is a vector or array. 2, we need to select a size, and it turns out that that selection is important. It turns out for various theoretical reasons that good sizes are prime numbers. It just turns out that you tend to get fewer collisions that way. So we won't go into it, but mathematicians have looked into it, and in general, good sizes are prime numbers. Okay, we also want to typically choose the size of the array to be bigger than the expected number of entries. So typically we also want the size to be greater than the expected number of entries. Makes sense because if the size is less than the expected number of entries, for sure we have collisions at some point because the hash table will fill up. Okay, and then 3, we need to choose a good hash function. That randomly distributes the input from 0 to the size. Okay, it's no good. I mean, a very simple hash function is this: hash of name equals 0. It's a very simple and efficient hash function. Unfortunately, everything goes to entry 0, so it's pretty bad at randomly distributing the input. So mathematicians have spent countless hours and papers describing different hash functions, and we'll actually look at those next time, not this time. We'll just assume right now that we have some good hash function. And the fourth thing we need to consider is collision resolution strategies for when we get collisions. So collision resolution strategy. And again, it turns out these are pretty simple. Okay? In fact, so simple that in 2 to 3 minutes I can tell you the two most simple ones, which are separate chaining and linear probing. Okay, so going back to this example, what separate chaining says is we're actually not going to store the names in the vector. Instead, what we're going to do is we're going to have each entry in the vector be itself a vector. So what we're going to do is each of these things is going to be a vector itself. So into this vector would go Smiley and Yifan. So each time we hash something to a entry, all we do is we add the, in this case, name to the vector for that entry. So add name to vector for that entry, for that table entry. So it's just a pushback. So each one has some number of entries in its vector, and we just do a linear search in order to find the name. And as long as our size of our table is greater than the size of our input, what's the expected length of a vector? If our table size is greater than the number of entries, what is the expected size of each vector? 1. So on average, we expect the vectors to be 1. They won't always be 1 because there will be collisions, but in general, we won't have to search very many entries. Yes?
So are you saying whenever when to retrieve something from the hash function, you go into that vector and then you take the actual thing that you're trying to retrieve and you check it against every element?
Yes, exactly. It's just a sequential search. So EFON hashes to 4. I go to entry 4, and now I just do a linear search through that vector and see if EFON is there. She's either there or not. So we don't do anything special at this point. It's an unordered vector, and we just do a linear search. Yes? You could, but it's not worth it. Because as long as the size of the table size is greater than the number of entries, this vector should be very short. Okay, so it's not worth it. Let me just mention the other technique, and we'll get into it in more detail next time. The other technique is called linear probing. And it's also very simple. What happens is if there's already an entry there, we just start walking up. Starting at entry 5, we look for an empty space, and if we find one, we put the name there. So there we put Yifan. If we now had Brad here, and let's say that next came in Tiger, and let's say Tiger hash to location 4. 4 is filled, so we go and look at 5. 5 is filled, so we go and look at 6. It's empty. So basically, we simply, with linear probing, start a sequential search, starting at that particular place in the vector. We search forward. If necessary, we wrap around to the beginning of the array. And when we find an empty entry, we drop the entry there. So with linear probing, the names are physically stored in the vector itself, and we simply do this linear stepping through the array to find empty entries. We'll get into this in more detail on Thursday, but there should be enough to start you on Lab 4 should you want to get started on it tomorrow.